Hello. So I'm going to take you through N2 recovery system that we did last year to help you get going with N3 recovery subsystem. So this is a rocket. This is a rocket, and our subsystem goes right here next to the nose cone. So what happens? The ejection happens here and separation happens here. When separation happens, then the parachute is thrown out in the air, filled with air, and then the rocket can now descend softly. Common methods of parachute deployment. So we have spring system deployment, which you use a spring to, let me just go to the slides here. So I have added a link to take you to the slides. So this is something we did last year to understand the methods of parachute deployment. So spring deployment is this is the body tube of a rocket, and then the spring is loaded right here, as you can see, and then this is the cut. So when this cut is released, the spring pushes the parachute outside, breaking the cork cover lid, hence releasing the parachute. So this is by okay, I can't remember the exact rocket team, but it was built. So this is the spring system deployment, and then advantages and disadvantages you can go through. And then by far the most used method of parachute deployment is pressurized gas motors, and particularly the hot gas deployment, also called the ejection charge deployment, and some call it pyrotechnic deployment. So hot gas deployment is what we use in Nakuja. We will get to it in a moment. And then we have cold gas deployment. Cold gas deployment, you use cold gas deployment use liquid carbon dioxide or nitrogen 4 oxide canisters. As you can see, these are their pictures. So can be servo actuated or pyro actuated. So actuation is the mechanism in which you release the gas from this canister. This is the canister, so that is the mechanical part of it. You can actuate it using a servo or pyro. So this is also another used method of parachute ejection. And then there's aerodynamic deployment slug. You can go through the slides to understand more. And then we are going to look at how Nakuja 2 okay, before that, let's first look at the general operation of a recovery system. So there are two major events. The trigger event. So the trigger event is how do you know when to deploy the parachute. So in Nakuja we have used the first and the second. We have used the first and second ways. So the first way, apogee detection. So when you detect apogee, okay, the rocket flight computer has sensors, BMP sensors and MPU. So these sensors are calibrated to give the altitude, the velocity, acceleration of our rocket. So these readings can be monitored, and then you can know, for example, when I get to 500 meter height above the ground level, then I should deploy the parachute. So this is using altimeters to detect the apogee, and then you you deploy the parachute. The second way to know to deploy the parachute is an uplink signal via Wi-Fi or LoRa technologies. It's also commonly known as manual override, where from the ground station you deploy the parachute by the touch of a button. So this has been worked on by last year's telemetry team. They worked on Wi-Fi manual override using the MQTT protocol. We as the recovery team last year, we worked on LoRa manual override. However, we did not get to test it on the flight, but we did quite a number of ground tests. So the third one and the fourth one, timer based and motor ejection. These are all we haven't tried these ones. So timer based ejection is where you use a brake wire. So a brake wire is a wire that snaps and it's connected to the electronics and the microcontroller. Due to changes in voltages when the wire breaks, you can tell the microcontroller can tell that the rocket has taken off. So once the rocket once that happens, then there is a countdown timer that begins to count down, and then at the end the parachute is deployed. So let's say you've set the countdown to 30 seconds. So once the rocket takes off, the brake wire breaks, the countdown begins, and then after 30 seconds the parachute is deployed. So this one is also used, but we haven't used it at Nakuja. It has its advantages and disadvantages. It can be used to override all the others in case maybe you don't detect apogee. In case there's a problem in software, then timer based can come to your help. We also have motor ejection. Motor ejection is an interesting one. So in advanced rocketry in colleges in the US, they buy motors. Their motors are bought, and these motors have special features called time delay. So this time delay, it's not electronic at all. It's just by the design of the motor. Once the fuel burns out, then the fire spreads slowly to what they use for pyrotechnic ejection is called black powder. We don't use that. We use crimson powder at Nakuja. We've used crimson powder, so that's just an alternative for it. So this is just by design. We have like a you cannot set it on software. This is basically just the design of the motor. You can have a look at that later. So this first and second one is what we have done at Nakuja. Separation and ejection event. This is now the actuation. This now, let me just go back here. So separation is when the nose cone comes out, and now ejection is the parachute is blown out into the air and filled up with air, becoming a parachute now. Because when you stuff it into the rocket's body tube, it's not like a parachute, but once it gets out in the air, it gets filled up into an umbrella like shape and then becomes useful. So we have just looked at the separation. So these steps for separation, I think it's best if I show them with this diagram. So this is our MCU. Our MCU is a microcontroller. So our MCU is powered, has to be powered. So it could be powered by a different battery, or you could just use this same battery here, the LiPo battery that we're using for the parachute system. You just down convert it, because like what we normally use is 11.1 volts nominal voltage LiPo battery. So you down convert it to 5 volts, or 3.3, and then it can now power this ESP. So this is this left part is how you power the ESP. And then at the ejection pin, these lines have just drawn touching the image of the ESP controller. It is not it does not mean that the ground is this pin. No, I've just drawn like an abstract representation of how you would connect it to the ESP32. So the ejection pin, let's say, is just this pin. So the ejection pin is what goes high when you want to deploy. So this trigger event, for instance, when the apogee has been detected, or even you've received an uplink command from the ground station, then this microcontroller sets this pin high. When this pin goes high, then it turns on this is an n-channel MOSFET. So for Nakuja, we used this one particularly, IRL 540N, as our MOSFET. It gets turned on by the 3.3, the pin, the output pin on ESP32 is sufficient to turn it on. So when it's turned on, this becomes a closed circuit, this one here. So once it's a closed circuit, then as you can see, current will go through this part. So this is our pyrotechnic chamber. So this color here, I think it's blue. So this is a crimson powder. It's just an representation, illustration. So crimson powder is a special, we will look at how to prepare it. Crimson powder is a special pyrotechnic substance. So when it gets easily ignited by a very small amount of heat. So what happens when, and the nichrome wire is also nichrome wire is a special type of conductor that it becomes heated by a small amount of current. When it becomes heated, it ignites the crimson powder, and the crimson powder is a pyrotechnic substance. That means it explodes. When it explodes, that's why it's called hot gas deployment. It's a very hot gas which is at a very high pressure. So this when this gas, so let's have a look at this again. So when the pin goes high, the ejection pin goes high, and the circuit is completed. Look, try to visualize these chambers, the parachute bay, which it usually is. So the hot gases will expel the nose cone, it will push it out, then it will also push the contents of the parachute bay out, and then now the parachute will be exposed to air, and it will fill up into now our working parachute. So that is what happens. This is the actuation. So this is now called pyrotechnic actuation or hot gas deployment. So you're using pyrotechnics to explode, to expel out the parachute. So I hope this was clear enough. So we are going to next look at the ground test that we did at Nakuja. So I'll just play this one so you can have an idea of what pyrotechnic is. So these are ground tests. We carried many of them. So there it goes. So that is ejection. So these ones we had not secured the nose cone and the parachute. We just we had not tied anything to anything. So this is just to show you how the ejection happens. And the aftermath is pyrotechnic being a hot gas deployment mechanism. That is why it causes this to burn, which is something that is undesired. Later we look at what we did to solve that. And So crimson powder, these are the ingredients, how to prepare it. So this one was prepared by one of our people at Propulsion. So Propulsion helped us prepare this. So you'll just have a look at that procedure if you'll be looking at pyrotechnic deployment. And then an important part of parachute deployment, the recovery system, is the dimensioning the parachute. So I have linked other slides here. So how to dimension a parachute. A very important parameter in calculating the dimensions of the parachute is the air density. So air density at different places. So this one was at Isiolo, where we did our rocket launches last year. So this is the altitude of Isiolo above sea level. And then from the charts, the ISA model is what is used to, it's called International Standard Atmosphere, and it's commonly used when you want to get the density of a particular place. It's quite reliable, so you can look at it. For instance, we have this one. So this is a chart that uses the meters. Okay, it has meters and feet. You can choose between the metric system and the US system. So like this one is 1127 meters above sea level. 1127 meters, you can now come and have a look at it. 1127 meters is like this. 11 is between here and here. So we expect the density. This is relative density. So relative density, you can get the actual density by using the relative density and the absolute density. So okay, let me just go here. So these are the values at 1000 and 1500. So the air density has to be between here and here. So this is for one chart. Another chart that is another you can have a look at this. This is an online calculator which you can also use. So like this one gave us to be 1.250 to be as our air densities. And then there is this formula that is used to calculate the dimensions of the parachute to use. So as you can see, the air density goes here, the coefficient of drag. They have several videos on how to size this formula, explaining it. You can have a look at them online. So we did an Excel formula to help you calculate this. So what you do, you feed it the parameters. For instance, the mass of your rocket, like in this case is 3. The air density in Isiolo is that. The coefficient of drag, we normally want it to be 0.75 going up. And then there is the gravity, which is 9.81. The terminal velocity is the velocity in which you want the velocity at which you want the rocket to descend. So terminal velocity, when you pick 5, you get the diameter to be 1.9 meters. So this is in SI units. Let me indicate this. Okay, as the meters, yeah. So you'll get the dimensions in meters. So this is quite a neat way to calculate the parachute size. And then this is also another chart by Apogee Components that you can look at quickly. It's a chart to help you know the diameter to use. So apart from that, okay, we have looked at parachute sizing, the challenges that we faced. So most challenges we faced were mechanical, like the parachute being tightly packed in the bay and having insufficient ejection charge force. The more tightly packed means you're fitting like too much material inside the parachute bay, and the crimson powder is not enough to eject it, because now it's tightly packed onto the walls of the inner walls of the body tube. So we want it to be moderately packed, and we want to have sufficient ejection charge force. So we use we try different quantities of crimson powder to see what is the optimal one.